Okay, so this is the second in the asynchronous meetings on statistics. This time around, we're focusing on how we summarize and graph data. Um, the thing that I keep trying to drive home with students on this is the idea that, and it's kind of a big one, when you summarize, and graphing is a form of summary, but when you summarize or graph, you lose information. And that is something you need to be aware of and that you have to make careful choices about. Um, because your most informative set of data is or presentation of the data is the raw data itself. So, like, if you're looking at a summary or you're looking at a graph and there's something you don't understand or you can't get from that summary or from that graph, what you need to do is you actually have to go back to the data set itself and look for that information. And you have to re-summarize the data to get the information that you want. Even in a data list, if the data list isn't captured correctly, one of the things that almost automatically gets lost is the time element. Because the data list is already somehow like a sense of a cross-sectional observation where it gets truncated in time. So, like, doing some sort of time series is like really difficult to capture, but that's probably the most informationally rich way to do a data set. Um, Anything other than time series gets you something where you've lost something along the way, and that's kind of a challenge. Now, the question is, it's like, what are we capturing and what are we losing? Okay, so when you get into summarizing and graphing, you're trying to capture different characteristics of the data. And typically, there's five that we're looking at. And these are the ones that I've listed here. It's going to be the center. Okay, so there's certain measures of data that get you like the middle of the data set. Those are typically mean, median, and mid-range. People like to say that the mode is the center, but really there's no sense of mode being central at all. Um, it can be that the mode can be all the way to the left or all the way to the right. So the mode's not really a description of center, but mean, median, and mid-range, and we'll get into more detail as to what those are definite measures of center. Um, Another thing that we try to capture in summaries and graphs is variation. This is like the spread of the data, is another way of saying that. The farther that the data spreads, the more variation it has. That sense of spread, though, is kind of imprecise. Like you can capture variation by looking at just simply range. How far is it from the lowest to the highest value? Or you can get a little bit more sophisticated using things like variance and standard deviation. Variance is a measure of like how far it is between items within the set. Standard deviation, the problem with variance is it's in the wrong units. So variance does give you a good measure of how variable things are in the set, but then it's not in the same units as the data set is. So this is why you have to take a square root of the variance and end up back to standard deviation, which gives you a measure of variability, okay? But it's in the units of the set. So that's where we get into that. So that's variation. Distribution is the third one. Okay. So these are the two that the students tend to confuse. Distribution and variation. This is the shape of the set. Okay, so like two sets can have the exact same shape, right? So these sets are distributed as like bell-shaped and symmetric, but this one might run from 0 to 10, and this one might run from 0 to 1,000, which means the standard deviation of this one is going to be small, and the standard deviation for this one is going to be large. So like you can have two things that have the exact same distribution, the same shape, and a radically different standard deviation in spread. And likewise, this can go the other way. Like you can have like a skewed left set that runs from 0 to 10, and you can have, sorry, that's skewed right. Oops. There we go. Skewed right set. And you can have a skewed left set that also runs from 0 to 10. Oop, don't do that. And the standard deviations here are going to be equal, but the distribution is definitely different. I mean, this one is way skewed the other way, and this one is way skewed that way. We'll get into skewness in a minute, but skewness is one of the, so when you're describing distribution, you tend to use, where is the mode? Where is the most frequent point? So where's the top of the curve? What is its sense of symmetry? Is it skewed left? Is it skewed right? Another measure of distribution is what we're going to call the interquartile range, which is like where does the middle 50% lie? Like school statistics like to use the IQR a lot. Like they'll give you like of acceptances, where is the first quartile and the third quartile for SAT scores. So like that's one to be aware of that gets used frequently to describe the distribution of scores. So, all right, so things that we're capturing: center, variation, distribution. The other two are outliers. And outliers are extreme values. They're not just unusual, they're extreme. So like if you have a picture, if you look at the distribution of something, so let's say we've got something that's generally speaking bell curve-ish, and then you got like a score that's out here, that's an outlier. Okay, it's like just removed from the general set. Like what could happen here is these guys could be unusual. Okay, but they're not outliers. They're still within the range. But an outlier is like further out. We're going to get a technical definition for unusual and outliers. Okay, that unusuals are more than 2 standard deviations from the norm, or unusual values. Outliers are going to be 1.5 times the IQR, the interquartile range, above and below the first and third quartiles. We'll get to that. Don't worry about that right now. But one thing to know is like if you make a histogram, an outlier looks like a broken tooth. It looks like there's the histogram, and then there's an open space, and then there's a broken like bar somewhere distantly from the main distribution. Times. So like just a quick thing on outliers. Like kids will sometimes think that like, ooh, the tallest kid in the class is an outlier, okay? And no, they're not. I mean, generally speaking, we don't have any outliers by height at Garrison Forest School. Like a few years ago, I had a softball player in the class who was extremely tall for her age and all of this, but she wasn't an outlier. She still fit within like normal ranges here. She just was tall. So that's confusion. Yao Ming, in comparison to the Chinese population, is an outlier. Okay, if you like watched the Olympics a few years ago, when he was playing on the basketball team, and the Chinese contingent was walking into the stadium during like the parade of what do you call it? The Parade of Nations. There's like the whole Chinese contingent is like in this kind of reasonable uniform height group, and then there's him with the Chinese flag like feet taller than everybody else. It's like you can actually visually see. It's like almost like they had a three-dimensional histogram there where you could see him pop up as not even close to anywhere else in height. He would be an outlier, but now he's not an outlier if you make the population like players in the NBA. He's unusual. He's tall, but he's not that tall in that population. All right. So there we go. So back to times. Times is the hardest one to capture because usually when we get data sets, it's truncated and we don't realize the time factor in it. Right now, times is a huge thing. Okay, so like if you look at COVID graphs, the y-axis is almost always time. So it's a data set over a time series. And we're going to see that like some of the things I'm going to describe later on as unusual graphs here are actually becoming frequently used in trying to describe COVID because the time series is so important. So the order in which data points occur is the thing that we're trying to capture in time. And like right now, capturing time in a data summary or a graph is like a really big thing. So when we lose some of the other things in the graph, we're actually picking up the times stuff. So it's actually even interesting because the whole move to doing 3-day and 7-day rolling averages is what's called a mollifier. And it's designed to try to smooth out the curve so that they can do some inferential work from it. And the idea there is that you're leveraging the time element of the data in order to smooth the data in order to make it usable in analysis, which is where you kind of get that sense where like calculus and statistics meet, because you can't do analytic work using calculus on a bumpy curve because you get all these points of non-differentiability. So doing a little deep dive there, but those of you who teach some calculus and pre-calc stuff might be able to pull something there where like they're leveraging the time piece in order to make smoothness so that you get differentiability and you can draw related rates and things like that using calculus. So, all right, let's back up and get to normalcy here. All right, I'm gonna maximize the notes for a second here because I'm going to get into some tables and things like this. So ways that we summarize. A pretty common way is using frequency distributions. This is what your kids know as like t-tables. So you have like a set of values, right? And then on the right-hand side, you have like the frequency within those values. Now, something to be aware of is like the choice that you have to make is the classes. So like the set of values are not usually just single values, they're usually a class of value. And how many classes becomes like the question. Because like if I do a whole bunch of classes, then I just get like this big 1-1 broken tooth 1-1 type thing. If I do too few classes, I don't get any information from that. So statistics gives us this thing that's called Sturgis's number. And it's not something that you need to do a deep dive with your kids, but it's right here. Sturgis's number is this formula, 1 plus the log base 2 of n. And the idea here is like that'll give you the number of classes that you need to have. And in order to get some sense of the shape, it also helps to pick up outliers, because like if you have an outlier, some of these frequencies will go to 0 and you'll clearly see, oh, there's an outlier there. So like, I'm going to bring up the calculator here for a second. All right, and show like I did it for 100 here. So like if you have 100 data points, take 1 plus, now the calculator doesn't do a log base 2, so you have to do log of 100 divided by log 2. You can also do that with a natural log. It doesn't matter. It'll work either way. And that gives me that 7.643 that I have here in the notes, which means that I should probably use 8 classes if I have 100 data points. Okay. It gives me some sense of this. Why Sturgis's number works is like a whole topic for grad school. The real answer is not everybody who builds a frequency table uses Sturgis's number. And honestly, it's just like you use enough classes to be useful. If it starts getting too thin, you subtract the number of classes. If it starts getting too wide, you add more classes and so forth and so on. Okay, so I want to show some little details here. This is continuous quantitative data. So like I have a frequency table here. You'll notice that each class ends with a 20 and like ends and begins with the same number because we're continuous, right? So we have to capture everything up to 20 and everything below. Now, you might want to add some clarity there, that like 20 belongs to the class above, like 20 is in this class itself, but not in this class, right? But we also need to say that like 19.99999 is in the lower class. So you could add some clarity to the table, but the fact of the matter is that when you're doing continuous measurements, the probability that a data point actually lands at 20 is like 0. Okay, like nobody weighs exactly 47 pounds or 147 pounds. Let's do that. They either weigh slightly below that or they weigh slightly above that. So picking specific data points there usually doesn't matter if you're working with real data and not just like reported numbers. Discrete though, you definitely want to end so that one whole number ends at 19, the next whole number starts at 20, because when you have discrete data, you can't have 19 and a half cats, so the classes make more sense that way. You could do frequency tables with quantitative data, okay? So the problem herein becomes like the order in which you put them. You want to make sure that you're not communicating something by the order that you're putting them in. But at the end of the day, it doesn't matter. Ultimately, sometimes it's helpful to have them from greatest to least and things like that. We'll see how that looks out in physical graphs a little bit later on. But quantitative data, it doesn't matter the order that they're in. All of these can be converted to relative frequency distributions. But you're going to see something here. Like in frequency distributions, things like time is lost, right? You don't know time, and you also lose specific data points. Like we now know that there's 12 data points that are between 10 and 19, but we don't know specifically what those data points are. So you lose some of that information. Okay, so like as we're seeing the summary, you're losing stuff. Frequency, relative frequency is that it's the percentage of the whole. So instead of saying, and we have 13 data points, we might say that it's 3% or 7%. Typically, you usually give it as a decimal. Sometimes you'll see them as percentages there. But to lend clarity, you tend to use decimals because of the decimal problem, where if I end up with one of these being like I said before, like 0.25%, that just gets weird and not useful. But here, now you're not only losing the data, but you're also losing like how many data points were there at all, right? So like, was this 3% out of a million or 3% out of 7, whatever. Oftentimes in here, they'll make an n. So like they might say n was 4,000. So this is the relative frequency with an n a sample size of 4,000. And then one of the exercises that you can actually do with kids is have them build relative frequency from frequency tables. And then if given the n, can I get back to the frequency table? Like what can I reclaim from information loss given different components of a summary? Now, tables are great, but they're actually like really horrible for the human brain. Especially if there's like large numbers or small numbers. An exercise that I like to do with the kids is actually like have them look at the chalkboard as 0 being one side and a billion being the other side, and then put a mark where a million is. And it's amazing how many of them will like put the million mark like on the left-hand side of the board or in the middle of the board, and they'll just totally miss it because they can't represent big numbers in their head. So this is why visual representation is so important. But again, the problem with visual representation is information loss. All right, so the workhorse for visual representation for one variable data sets is the histogram. Now, histogram is a fancy word for bar graph, and there is a difference between the two. Histograms, there's certain things that you want to note. One, you always use classes on the bottom. You also have them touching each other, okay? Because you get, distortion if you don't have them touching each other. There's also a sense here of, when you're working with histograms, you want to have the classes all be the same width. Okay, so that though will give you a really good quick view of the distribution of a data set. Like this thing is like hugely skewed left. It has, a big bubble on the right here, which might indicate some sort of upward fence in the thinking. But you get a lot of information from this, but also like individual data points are lost. It's similar in information that's given in, the frequency table though, the frequency distribution. Now, what I'd like to do here is to bring up the calculator for a little bit and just show how do you deal with a frequency distribution, turning a frequency or a data set into a histogram. And I gave like step-by-steps here. So I threw in a data set. So to build a histogram in the TI-84, you hit Stat, you go to Edit, which brings you up the spreadsheet. Okay, and we have one variable here, so we're just going to put it all in L1. There's 1, 2, 3. I'm not going to read these off. I'm just going to do it. Okay, so there's my data list. It's all in L1. Usually I advise students like to always start by going back to the main screen so you're not like putting stuff within stuff on the calculator. You don't actually have to do that here, but it's probably always a good idea. Getting back to the main screen is always second mode. And then I want to have it produce the histogram. So I'm going to have it do a stat plot. So that's second y equals. All right, so like there's a list of plots here. The calculator can actually do I think it's 4 plots. No, it's 3 plots. The calculator can do 3 plots. The fourth option is just turn all the plots off. The fifth option is to turn all the plots on. Right. So we're going to do plot. We're going to make this plot 1. I have to turn the plot on. The histogram bar is that one right there. And I'm doing this with list 1. You can change that if you used other lists. And currently the frequency is 1. Okay, because each of these values only has a frequency of 1. We're not using a frequency list here. Okay, so to make the plot, you have to play with the window. So we're going to go with zoom. Oops. Shoot. Not sure what I did there. Let's get the plot back up. Okay, so go zoom. There we go. And we want to go down to number 9. And 9 is like the statistical zoom. So what it will do is it will force the window to be the size of your plot. Okay, so it'll fit the window to the plot. You hit 9, and it draws the histogram. Okay, now if I go trace, that tells me down here that this bar is running from 1 to 8.5, and 8.5 is not included in the bar, and that there's 9. That bar represents 9. The next bar is from 8.5 to 16 with 5. 16 to 23.5 with 5. Now, the calculator picks the width of the bars. Okay, what does it use to pick the width of the bars? It uses a pretty strict interpretation of Sturgis's number. And so actually don't have the students do anything to this, because usually these histograms are pretty good and will give you valuable information like outliers and so forth. So just to like give you an idea of what I mean by outlier, I'm going to go and I'm going to re-edit the list. And something that would be like way outside the bounds here would be having maybe 105 as an item in the list. And now I'm going to go zoom 9 again. And you'll see it redid the histogram, and there's that broken teeth idea. There's no bar here, no bar there, no bar here, and one guy hanging out way out there. That's clearly what an outlier looks like in a histogram. Okay, so there you go. There's some thoughts on that. So that's the notes there. Let me bring this back up full size so we can keep talking about this a little bit. You can also do histograms with relative frequency. So instead of having it represent frequency values, you're now dealing with percentages. The relative frequency histogram and the frequency histogram have the exact same shape. So the shape should not change if you go from frequencies to relative frequencies. The only thing that changes is the y-axis. The scale changes from 0 to 1 as opposed to 0 to the n, the size of the data set. So that's just something to be real about. Creating a relative frequency histogram using the calculator doesn't work as easily. So just to be aware of that. It can be done, but it's not a whole lot that I would spend time working on. Okay, so this is opposed to bar graphs. Bar graphs are qualitative, not quantitative data. Okay, so histograms, quantitative, bar graphs, qualitative. You might use a bar graph if you have discrete data. Okay, that's possible. Now, there's nothing that says that the bar graphs actually have to touch each other. I just tend to do that. There's no distortion that's caused by that, but you can do that. The problem with a bar graph is that the location of the bars is arbitrary. There's no reason to have red to the left and blue where it is. I mean, it's just like, we do that. I mean, I made a rainbow here. Great. But if like I was doing things like data on race, there's no reason to have like alphabetical order or something like that. And in fact, that might cause some skewing of perception. So What people tend to do when they're doing quantitative or qualitative data is they tend to do what we call a Pareto chart, which I'm going to take the exact same information in this bar graph and then put it in a Pareto chart, which is you order them from greatest to least. And that gives you a little bit bigger of a picture as like, how is the distribution? What's the difference between ones? And it sometimes actually creates a more attractive graph too. But I think that it's easier for people to visualize how far things are being stepped down when you change from one class to another using a Pareto chart than it is if you're using a bar graph. So this is probably recommended if you're going to do something with qualitative or discrete data. It just kind of makes things there. And, you know, hey, colors, okay, great. Colors are always attractive to people. So let's talk a little bit about distribution and what graphs look like. I've made some TI graphs here. So uniform distribution is like each class is roughly the same frequency. Now I know that there's like bumpiness to this, but the bumpiness here is just caused by like usually a less than 5%. So this is where you get that less than 5% chance of differentiation between them. I mean, there's probably a sense where that's probably too high. Most of the data values are around there, some a little bit below, some a little bit above. But if you kept sampling and sampling in this population, it would probably come out like really close to that line. So this is what a uniform distribution looks like. Okay, so uniform is something that happens like when you roll dice, right? You want each of the outcomes to have equal frequency. Playing cards, things like that would all have a uniform distribution. Most things have a bell-shaped and symmetric distribution because of central tendency. Like there is an average human height and things like that. And we tend to go in equal directions from there. So bell-shaped and symmetric curve is going to look something like this, where the mode is equally distant from both sides. And the increase and decrease is the same in both directions. So things that are like the t-distribution and the normal distribution and binomial distribution are bell-shaped and symmetric. So like the generic term is bell-shaped and symmetric. Those are specific distributions that have that shape. Okay, so this would be a curve that we would consider to be skewed left. The skew is about the tail. Okay, so this is a skewed left curve. Now that's counterintuitive because the kids want to say, okay, the bubble is over here, that's to the right. So we say that the skew is where the bubble is, but it's not, it's where the tail is. All right, so let's get as to why that is. Okay, so the reason why we do this is that, like, okay, you have to kind of do some imagining here. And imagine if you were to see this as like a pile sitting on a board. And what you would have to do in order to make it balance is you'd have to kind of put like the balance point like here, okay? Maybe a little bit off, but that balance point is the mean of the set, whereas this is the mode. Okay, so if you look at a symmetric curve, mean and the mode and are both in the same place. What we've done here is we've pulled the mean to the left of the mode. So this is why we call this skew left. Another way of looking at it is usually when you have this type of data set, there's something that's causing an upper bound here. And that's why stuff is bunching up on the right-hand side. So what's going on here is that the data is like running into this wall, and the normal part of the curve is here to the left. The abnormal part, the truncated part of the curve, is being caused by this wall, which causes it to bunch up here. So what would normally be happening is skewed to the left. What causes things like this is like an unnatural upper bound. Grade distributions tend to be skewed left, because our students, very few of them get like zeros, okay? And if with 100 up here, our students tend to bunch up near the 100, because you can't get higher than 100, and the natural minimum score is probably somewhere around 50-ish, okay? So like, if you kind of think about this, you're going to have the middle hump being somewhere, like around 80 or 90. And if you took, like, let's say 85 to 50 would be a 35 range, right? So let's say 85 is the natural center here. That's a, 35 range. If you take 35 more than 80, you're getting to 115, which means all of this data that's above 100, the 15 plus, is getting bunched up into this section, which is why the whole data curve is actually skewing left. All right, so likewise, you can have a skew right. All the same arguments hold. Big bump on the left-hand side, tail is on the right, so this is skewed right. Something that would cause this to happen would be like student absences, right? Absences. Okay, like this is the hard zero, right? You can't have less than 0 absences. So you're going to have this bunching up on this end. And then, as you're going further away to the right, you're going to get it trickled down to something. So this is like bell-shaped and skewed right. So I know it's counterintuitive. Students like to want to say that the skew is where the bubble is. The skew is not. It's because you're pulling the mean away from the top of the bubble. And in the first graph, you're pulling the mean to the left. And then the second graph, you're pulling the mean to the right. So that's part of your idea of distribution. And you can see distribution in histograms. And that's one of the reasons why we use them. All right, so other one variable graphs. If you're doing like discrete data, a common one is a dot plot. A dot plot is just basically a visual histogram with discrete data. Each dot represents 1 unit in frequency, or could be multiple units. It's an easy way to do a histogram. Stem and leaf plot is another quick way of doing the histogram, right? So each of these is the first digit in a data point, and each of these is the second. So like if I'm reading this row, these would be the data points 20, 21, 23, 23, so forth and so on. Here you're making classes by size 10. It does, if you kind of look at it sideways, make like a pretty cheap histogram there that can give you pretty much the same idea as a histogram could. One of the advantages of a stem and leaf plot over a histogram is that you can actually recover the entire data set. You don't recover time series or anything like that, but if you rebuild the data set from the stem and leaf plot, you can actually do it. So information loss is minimized with that, but it forces you to have like classes of width 10, which doesn't necessarily line up with like the whole Sturgis's number in outlier reality. It would probably though still do a pretty good job of picking up some of the outlier stuff. But they're fast, they're easy. They're not commonly put into print because most people tend not to understand it without additional explanation. Pie charts, we've seen, most of us know how to do. The the areas there. It gives you a good visual representation by area. Again, they're pretty good for things that are like quantitative data, and it gives you a sense of portion of the whole. So that's like an advantage over the bar graph there, is it's like what portion of the whole. This has been something like as we've been dealing with police action and Black Lives Matter and all of that, there's been a lot of pie chart work in that because they're trying to show like, you know, out of the whole, what percentage have experienced this event out of the whole of, you know, that's a pretty useful territory for pie charts. So they've been used a lot in that reality for that summary. Okay, frequency polygon, I would say, is an uncommon graph until we came to, what do you call it? COVID reality, because it's like the one that gets used everywhere right now. So frequency polygon basically says, okay, this is people who are 39.5 and below. This dot covers the people from 39.5 to 59.5. This dot covers the people from 59.5 to 79.5. This dot is everybody from 79.5 to 99.5. So it's like, instead of building the histogram, you're building it as a polygon. And it's always looking left. So this dot, if you were to redo this as a histogram, you would end up with this shape. If that makes sense. So that's kind of like how the thing would compare to a histogram. Now, the reason why I say that in COVID this has become like the dominant thing that happens is that what we've done is we've used this to represent time series. And we put time on this axis, and then we start making these dates. So this would be like day 1, day 2, day 3, day 4, day 5, right? So forth and so on. And then what happens here is this is like, okay, there were how many cases were found between day 1 and day 2? Well, it's that dot. And then between day 2 and day 3, and day 3 and day 4, and then all of a sudden we get these case graphs that like look like this. I think currently it tends to look like, right? And that's actually a frequency polygon with date on the left and cases going up and down. So this thing is like one of the two most common graph types used in the whole COVID discussion. The other one that used to be viewed as somewhat uncommon is the next one here, which is an ogive. Okay. Yeah, that's actually pronounced ogive. Spelled ogive. So this is a cumulative graph, okay? So this point is the amount of data that's between 49.5 and 69.5. This point is the amount of data between 49.5 and 89.5. This is the amount of data between 49.5 and 109.5. So if you're noticing, this thing is cumulative, right? And each of these data points must be above the one prior to it. So what this gives me is kind of a rate of growth. So when the slope is high, over this period, growth was large. When slope was low, over this period, growth was small. This graph is like another one that is being really frequently used in the COVID reality, because what they're doing here is they're again making this time, and usually the unit is days, and let's say cumulative deaths is like one of them that's big here. And if you watch, that graph tends to follow a curve that's looking like this. Oh, it's getting ugly. Let's draw a little closer here. And it's looking like that. We had a slow growth in deaths, followed by a fast growth in deaths, followed by a slower growth in deaths. But this is cumulative deaths overall. Part of the reason why is that this starts showing what's called a logistic curve. And it gives us a sense of where we are in the process, and if we're speeding up or slowing down, which has to do with like rates of transmission and things like that. So this is a really common type of curve that's going on. So in fact, these curves that you're seeing that are cumulative are actually what are called ogives. And that's as opposed to the non-cumulative curves, which are day after day, which are frequency polygons. But these I would have typically taught as uncommon graphs, and yet they're the ones that are the go-tos right now for describing the whole COVID reality. Something that we want to recognize is that graphs can sometimes be misleading, and there's two major ways that that can happen. So let's take, like I have a bar graph here, and the problem here is that my bar graph starts at 9100. And what this looks like is it looks like these are substantially different in height. And that you would get a sense that there's a statistical significance of the difference between A, B, C, D, and E, and that this distribution is saying something that's meaningful. If I take that same graph and I use the same data to create both of these graphs and rescale this down to 0, this graph actually looks like this. Which, yes, it's still going upward, but not as significantly. This could really be seen as a uniform distribution across these 5 groups. There's no real evidence here that there's anything statistically significant about the difference in these 5 groups. Whereas if I have product E, I might want to use this graph to say, hey, I'm much better than product A, where this graph definitely says there's no real difference between them. This is the fair graph. The fair graph starts the y-axis at 0. You want to be careful to look at that y-axis number, and also to make sure that they're not doing like one of these that puts like a truncation in the graph, because if they do that, that's the same skewing of the data or biasing of the reporting. Another one that does, it's a common mislead, it's in pictographs, is that when we try to make something look a multiple larger, we scale in both dimensions. And here, what I end up with is making a graph that is 9 times larger when it should only be 3 times larger. Okay? So the fair graph would be something like this, to have 1 versus 3. This is something to talk with students about. There's a lot of different ways that graphs can be skewed and misleading, but these are the 2 big ones. Either changing the y-axis in a way that's not fair, or by changing pictographs in ways that are just expanding large and small. Okay, the other big workhorse that's used in statistics is a scatter plot. And this is used when you have a 2-variable data set and you're trying to show correlation between those 2 variables. So you might have a list of students, and these are their SAT and ACT composite scores, and we want a scatter plot for that. So again, I'm going to bring up the calculator to show how this would work. So let me bring this. Whoops, you don't need to see my emails. Sorry about that. Let's get the calculator up here, and let's reset everything so that we're not working with old data. We're going to go stat, edit, and I'm going to put the SAT composites into list 1. And we're going to put the ACT composites into list 2. And the way I get to the scatter plot is I go second y equals, turn the first plot on. This is the scatter plot. I'm going to do that with list 1 and list 2, and I can choose which mark I use. I tend to like the plus sign. You could use the box, you can use the dot, it doesn't matter. Again, you're going to use zoom 9 to have that display, and this will give you the scatter plot. So the x-axis here is the SATs, the y-axis here is the ACTs. Generally speaking, looking at that graph, I would say that as I go right, this graph goes up. So we would say that this is a set that looks like it is correlated positively. Just to kind of play with something to show you what it would look like otherwise, I'm going to go into y equals, and I think I can do this. We're going to try a little experiment here. If I go plot 1 and make it negative L2, no, it's not going to let me do that. All right, so let's try this. Let's go to the main screen. We're going to make, we're going to take negative L2 and store that in L3. Okay, and then I'm going to go to my stat plot, and in the second list here I'm going to put L3, which is the negative for L2, and then hit zoom 9. Zoom, crud. Okay, zoom 9. There we go. Same plot, but now it's all the negative values, and like you can see negative correlation now. That the plot now seems to be going down and to the right. If you don't get an up and to the left or a down and to the right, you would say that these don't appear to be correlated at all. So there's no evidence of correlation, or it doesn't exhibit correlation. But the scatter plot is to 2 variable data sets as the histogram is to 1 variable. It's the go-to kind of it's the go-to graph that we use to represent those data sets. So big takeaway is always that when you do a graph or you do a summary, you're always losing information. To track what information is being lost so that you know what decisions you're making when you're choosing which graph. And that's it for today. I think I ran pretty close to an hour here, so I'm not going to throw any exercises with this. But, you know, if you got questions, either email me or bring it to the next synchronous session, and we'll go with this. I hope this was useful to you, and we'll do another one. Hopefully within the next week, you should see it come up online. All right, thank you.